Chapter 26, Circuits. It covers works, energy, and electromotive force, calculating the current in a single loop circuits, multi-loop circuits, RC circuits. You can find them in a timeline: work, energy, and electromotive force. Pumping charges, electromotive force. A device that by doing works on the charge carriers maintains a potential difference between a pair of terminals. We call such a device an electromotive force device, and the device is said to provide an electromotive force, which means that it does work on charge carriers. A seat of electromotive force: battery, electric generator, solar cells, thermal piles, electric ears, human being. They all perform the same basic function. They do work on charge carriers and thus maintain a potential difference between their terminals. An electromotive device is sometimes called a seat of electromotive force. The term electromotive force comes from the outdated phrase electromotive force, which was adapted before scientists clearly understood the function of an electromotive force device.
Most batteries consist of two different materials in contact with an electrolyte. We'll use this pair of windmill arms, each containing 4 different metals, to show how the voltage of a simple battery changes with different pairs of metals. A trough of dilute sulfuric acid beneath the windmills provides the electrolyte. We'll dip different pairs of metals into the acid and observe the voltage developed in each case on this voltmeter. Here is copper and copper. Here is copper and iron. Here is copper and zinc. Here is copper and lead.
This pair of different metals has been twisted together to form a simple thermocouple. If we hook the thermocouple to an ammeter and place the tip near a flame, current flows through the ammeter. The closer the thermocouple gets to the flame, the more current flows.
Work, energy, electromotive force. This is a circle. We can present the electromotive force of the device with an arrow that points from the negative terminal towards the positive terminal, as in the figure. The device also produces a current around the circuits in the same direction, clockwise in the figure. A small circle on the electromotive force arrow distinguishes it from the arrows that indicate the current direction. Within the electromotive force device, positive charge carriers move from a region of low electric potential, and thus low electric potential energy, at the negative terminals to a region of higher electric potential and a high electric potential energy at the positive terminal. This motion is just the opposite of what the electric field between the terminals, which points from the positive terminal towards the negative terminal, what causes the charge carriers to do. So there must be some sources of energy within the device, enabling it to do work on the charges and thus forcing them to move as they do. Chemical energy, mechanical energy, biological energy, thermal energy can transfer to electromotive force, or of course it's solar energy. Let us now analyze the circuit of the figure from the point of view of works and the energy transfers in any time interval dt. A charge dq passes through any cross-section of the circuit, okay, such as AA prime. This same amount of charge must enter the electromotive force devices at its low potential end and leave at its high potential end. The device must do an amount of work dW on the charge dq to force it to move in this way, from low potential to high potential. We define the electromotive force of the electromotive force device in terms of this work. This is the work you done. This is charge, it moves. So electromotive force of these devices equal to dW over dq. In words, the electromotive force of the electromotive force device is the work per unit charge that the device does in moving charge from its low potential terminals to its high potential terminals. The metric system unit for the electromotive force is the joule per coulomb. We define that unit as a volt. 1 volt is 1 joule of 1 coulomb. An ideal electromotive force device is one that lacks any internal resistance to the internal movement of charges from terminal to terminal. The potential difference between the terminals of an ideal electromotive force device is equal to the electromotive force of the device. A real electromotive force device, such as any real battery, has internal resistance to the internal movement of charge. When a real electromotive force device is not connected to a circuit and thus does not have current through it, the potential difference between its terminals is equal to its electromotive force. But when that device has a current through it, the potential difference between the terminals differs from its electromotive force. We will discuss such real battery later. Look at this, okay? This is a battery. This is a battery connected in opposite direction. This is positive, negative. This is positive, negative, okay? What's happening, okay? The chemical energy lost, this battery, okay, can work done by motor, make the motor a mass M, and can be thermal energy produced by resistance, and can transfer to a chemical energy stored in battery A. Calculating the current in a single loop circuit. This is a single loop circuit. Okay? We use the energy method. This is energy produced in an electromotive force device equal to, by definition, the W, the work done is epsilon dq. It moves dq from negative to positive with the work dW, okay? And the dq from this point of view is I dt. This work done by the C. And Q equal to I squared R dt, okay, is the thermal energy dissipated from the resistor, okay? I squared R power multiplied by time dt is Q. They should be equal because of energy conservation. So we make this EI dt equal to I squared. and we get I. I equal to epsilon for R. This is for ideal electromotive force without internal resistance. And actually, they have internal resistance. So the I equal to epsilon over R plus R. R is the internal resistance of the electromotive force device. Second, we use the potential method. We have a loop rule. The algebraic sum of the changes in potential encountered in a complete travel of any loop of a circuit must be zero, because the same potential at the beginning and the last, so the potential difference is zero. Resistance rule. For a move through a resistance in the direction of the current, the change in the potential is minus IR. In the opposite direction, it is positive IR. Now, we look at this current, I, and resistance. Definitely, this is a high potential, this is low potential. If we go through along the I direction, the potential goes lower, that's minus IR. If we go this direction, look at it, the potential goes high as IR. Electromotive force rule. For a move through an ideal electromotive force device in the direction of the electromotive force arrow, the change in potential is plus epsilon. In the opposite direction, it is minus epsilon. Now, we go along this direction, the potential increase, epsilon. If we go this one opposite the direction, we get a minus epsilon. This is a single loop circuit, okay? We can assume a current arbitrarily. In this case, we assume it's clockwise. Of course, you can assume the opposite direction arbitrarily. We also can assume a direction, a transverse arbitrarily. You can calculate in this direction or opposite direction. We get the same answer. Now let's try this one. We suppose I is this direction as indicated in the book. Starting from point A, we go this along the direction of this arrow, we get the potential increase. We go this direction, okay, clockwise, increase. And go this one, so the resistance along the direction of current, get a minus IR. And we go to a 0. From this one, we get I equal to epsilon over R. Now, we do different. We don't go this way. We go opposite direction. Can we? We go counterclockwise. I start from A. We go against I, we get IR. And we go against epsilon, get a minus epsilon. So plus IR minus epsilon, we get I equal to. So they are the same. The answer does not depend on the direction you choose. Okay? Now, we do different way. We assume the opposite current, okay? And not this direction, go opposite direction, okay? And what happened? And we start from here. We can choose anyway, okay? Now, we choose the clockwise, this one, from A. So we go to epsilon against I plus IR, go with 0, okay? Epsilon, and you get I equal to minus epsilon. Or, you see, well, this is positive and negative. Is the same or not? It's the same. Why? Because in this case, you assume the current this way. So that means real current is this way. And here, we assume the current this way. You get a negative number, that means real current is this way. The same as the previous answer. Now, under this conception of current, we do another transverse. Okay, we go counterclockwise. We start from A, go this one. This should be minus IR. This should be minus epsilon. Okay, we get R equivalence. Under this assumption, we get the same thing. Okay. Other single loop circuits. This figure shows a real battery with an internal resistance R wired to external resistors of resistance R. And analyze this one, start from A. We start from A, okay, we go to battery, so the potential goes up. Okay, this is potential. And we go through the internal resistance, it drops, okay, because this is minus IR. And when you go this, along the current, get another minus I, it go back to the original VA. So VA plus epsilon minus IR minus my big R, you get VA. You cancel the VA, we get R equals epsilon over R or R. That's the one we just mentioned, okay? Potential difference between 2 points. I want to find the potential difference between 2 points, like B and A. From B to A, okay, I go this one, okay, VB, okay, I go this direction, minus IR, because I go through equal to VA. So VB over VA equal to RA, IR, okay? Also, you can go this direction. This direction is this plus IR minus epsilon. We get the same thing. You get the same thing. So equal to I over R. This is I over R, I equal to epsilon over R plus R. Okay? To find the potential difference between any 2 points in the circuit, start at 1 point and traverse the circuit to the other, following any plane, and add algebraically the change in potential that you encounter. You get it.
These two sets of batteries appear identical and show approximately the same reading on a voltmeter, but there is a difference. When a light bulb is connected to this set of batteries, the bulb lights and the voltage of the batteries remains about the same. When we do the same with this set, the bulb fails to light and the voltage of the batteries drops to nearly nothing. This set of batteries has been heavily used and has a high internal resistance.
We'll hook these 3 variable resistors in series with this battery and measure the voltage drop across each resistor to see how their sum compares to the applied voltage. The battery supplies a constant 6 volts. Let's go around the circuit and measure each of the voltage drops. The first resistor has a voltage drop of minus 0.9 volts. The second, minus 2.6 volts. And the third, minus 2.5 volts. The sum of the voltage drops, minus 6 volts, is the opposite of the applied voltage. Now we'll change the resistors and repeat the process. The first resistor now has a voltage drop of minus 2.2 volts. The second, minus 3.5 volts, and the third, minus 0.3 volts. The sum of the 3 voltage drops is again the opposite of the applied voltage.
Resistance in series, we have learned in high school. I will get, if we have 3 resistance connect in series, we can use an equivalent resistance, replace them, okay? And this number of equal resistance equal to sigma IR.
We'll hook these 2 identical wire resistors together in 3 different configurations and apply the same voltage to each. This ammeter will measure the current that flows through each of the configurations. Here is the current that flows through a single wire with 6 volts applied. If we hook the 2 wires in parallel, how much current will flow? Twice as much current flows as with a single wire. If we hook the wires in series, how much current will flow? Now only half as much current flows as through a single wire.
Here are 3 light bulbs. We'll hook the first bulb up to house current, then hook the other 2 bulbs in parallel to the first, one at a time. The brightness of the bulb stays constant as each is hooked in. Now we'll again hook up the first bulb, then hook the other 2 bulbs in series with it, one by one. How will the brightness of the bulbs change? The bulbs dim as each new bulb is added.
Resistances in parallel. We also learned in high school. We have 3 resistance connect in parallel, and you can use equivalent resistance replace these 3. Okay? And the relationship between is 1 over R equivalent equal to sigma 1 over Ri. Sample. The electromotive force and the resistance in the circuit in figure have the following values. Epsilon 1 equal to 4.4 volt, epsilon 2 at 2.1 volt, R1 2.3 ohms, R2 1.8 volt, big R 5.5 ohms. Question A. What is the current I in the circuit? This is very straightforward. Okay, we look at this. Okay, we from 8. Okay, we go counterclockwise from 8 to this one. So the first one it goes, we drop epsilon 1 minus epsilon 1. Okay, we assume the current in this direction. So whatever you can assume, as we mentioned before. So this one you come from up to down against the current. So you get plus IR. Okay, you go this one. You go to epsilon I1, big R, R2, and then second battery, you go to 8. And what we do is, we the counterclockwise this way, okay? This is minus epsilon. This is positive IR, positive I, big R, positive IR2, and positive epsilon 2, okay? So in this way, we can get I, get the I, okay? This is actually is, you go, you get dropped potential. You got increase, you got to increase, you got to increase, and you have another increase. You get the same level. We find I. Epsilon 1 minus epsilon 2 over R plus I1 R2. Also, we can do different way. Okay, we go clockwise. At the 8 clockwise, it goes, this is minus epsilon 2. This is along this one, minus I R2, minus R big R, minus I R1, and you plus epsilon 1. And so you go this way, you get I, the same as the previous, because you assume the same direction of current. Question B. What is the potential difference between the terminals of the battery 1 in figure? This is the one, battery 1, or these 2. That's, you know what to shoot. VB. This is VB. Okay. You go this along the current, you get a minus IR1. You plus epsilon, you get VA. Okay? So VA minus VB equal to epsilon minus IR. And then we know I. Okay? We just calculate. So we put the number inside. Okay? We get answer 3.84 volt. Multiple loop circuits. This is a multiple loop circuits. How many loops we have? This is one loop. This is one loop. Also, we have another loop, this big one. Okay, it looks like we have 3 loops, but actually, later on, you know, only 2 are independent. More than one junction. The judgment, what is the multiple loops? What is junction? Junction is more than 2 branches, at least 3, meet together at the junction. And that's B, 1, 2, 3. 1, 2, 3. So B and D are junctions. And A and C are not, because only 2. Okay, 2 branches is not a junction. Okay. Sigma I in equal to sigma I out, with the charge conserved. So the current get into the junction equal to current get out of the junction. No current, no charges from the junction or into the junction. Now, we choose the direction of the current arbitrarily, any loop. In this case, we choose I1, I2, I3. Okay.
The amount of current entering a circuit junction or node must equal the amount of current leaving the node. We'll use this setup of batteries, resistors, and ammeters to show that is true. The ammeters are set up to read the current flowing into and out of this circuit node. Here are the currents at the node at the first resistor setting. The total current flowing into the node is equal to the total current flowing out. Here are the currents flowing into and out of the node after the values of the resistors are changed.
Junction rule. The sum of the currents entering any junction must be equal to the sum of currents leaving that junction. This rule is often called Kirchhoff's junction rule or Kirchhoff's current law. The number of independent equations, including the number of junctions minus 1, because they are independent. 1 is not, so you total number of junctions minus 1. Plus the numbers of independent loops. Each loops we can write an equation. And these put together should equal to the number of the unknown currents. This is the rule. An independent loop must contain a new resistor or battery, at least, which has not been counted before. If they did, then it is not independent loops. Okay, then we do this one. This is multi-loops. How many loops? 1, 2, and big one, 3. Okay. How many junctions? Now, 1 junction, 2 junction. So we write the equation for current 2 minus 1, 1 junction. For example, we take D. If you take D, okay, I1, I3 flow in, I2 flow out. So we have I1 plus I3 flow in equal to I2 flow out. How about this one? Okay, a junction B, if we write another equation, is exactly equivalent to this equation. So only 1 independent. circle, we can have 1, 2, 3. Let me see that. We can circle B, A, D, B, this one. We start from here, okay. Epsilon 1 plus minus I1 R1 plus I3 R3 gotta be equal to 0. And another one, okay, B, B, D, C, B, this direction. So from here is minus R3, R3, minus I2, R2, minus epsilon 2 is 0. That's the three equation, okay? This equation have three unknown, I1, I2, R3. Principle we can solve in mathematics. You have asked question, how about the big loop? Of course, it's a loop. But they look at big loop, R1, R2, epsilon 1, epsilon, all have been counted before. So new stuff, no new stuff. So it's not independent. So in this case, we have three equations. Of course, if we don't count this one, we count this one. Second, we have these two, a new one. It's independent, okay? Anyway, in this way, we have three equations, have three unknown. This is a tedious work from high school, okay? So we can solve it, okay? Now, this is the answer again. Now, let me give you something. Physics. Suppose I3 is infinity. We cut this one. What happened? Look at this one. You have I3 is infinity. I3 is infinity. Okay? All right? And so this can drop because compared to have I3. So on top is epsilon 1 minus epsilon 2 R3 divided by okay, I2 plus I1. Forget about this. Okay? And I2, I3 drop this one. I3 drop this one. We get I2 equivalent to I1. And look at this one. This one is I3 is in denominator. So this is a 0. We get I3 equal to 0. I1 equal to R1. This is exact situation, right? Yeah. If they cut this one, of course I3 equal to 0. I1 equal to I2, okay? Sample. This is another multiple loops circuit. Pictures a circuit whose elements have the following values. Epsilon 1, 3.0 volt, epsilon 1. Epsilon 2 equals 6.0 volt, epsilon 2, epsilon 2. R1 equal to 2.0 ohm, R1, 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 R1. R2, 4.0 ohm. The three batteries are ideal battery without internal resistance. Find the magnitude and the direction of the current in each of three branches. So 1, 2, 3. First, we assume the current arbitrarily. Now here was one, assume arbitrarily. Okay? This is I1, this is I1. This is I3. In between is I2. Then we study from this one. How many loops we have? 3. 1, 2, and big 3. Okay. First, we take junction. How many junctions we have? Junction is 3 branches, A and B. Okay. So we write equation for currents is 2 minus 1 at point A. Which is when I3 in, I1, I2 out. So I3 equal to I1 plus I2. No more equation for current because only 2. The n minus 1 is independent. 2 minus 1 equal to 1 is independent. Only 1. Then you create the loop. Okay. The loop, we go the clockwise. Go this direction. So A minus I1 R1 minus epsilon 1 minus IR1, go to here, plus epsilon 2 plus I2R2 equals 0. And then we go this direction, okay? The clockwise, which is plus I3R1 minus epsilon 2 plus I3R1, go this, plus epsilon 2 plus I2R2 equal to 0. Now, is that, how about this loop? In this loop, all the resistance of battery has been counted, so nothing new. So it's not an independent loop. Three unknown, I1, I2, I3, three equation. So we can solve this one. This is a tedious work. I'll just give you the answer. Okay, we get I1, I2, 3. We look at this one. I2 is a minus number. That means the real current goes this direction. Okay. The ammeter and voltmeter. Okay. Voltmeter is measure potential difference. Okay. In order to measure potential difference and avoid to interfere the current, so it's connect parallel and the resistance should be much larger than R1. In that case, we can reduce the interference because of this connection. The current goes this direction. Okay. Ammeter, we measure the current, so it should connect in series. Okay. Okay. And in order to avoid to interfere that measurement, the R resistance, internal resistance ammeter must be very small. Okay. Ohmmeter can measure the resistance. Okay. And we have multimeter, so you can measure the ampere, voltmeter, and ohmmeter.
This galvanometer will be used to show the electrical connections that change a galvanometer into an ammeter and a voltmeter. Running a 25 milliamp current through the galvanometer drives it to full scale. If we want to measure larger currents, we must connect a shunt across the ammeter like this. The reading now goes nearly to 0 because the meter now requires 1 amp to go to full scale deflection. If we increase the current, we again get a reading. To measure voltage, we connect a specific resistance in series with the galvanometer like this. Now we have a 10-volt full-scale voltmeter, which we can use to measure the voltage of this 1.5-volt battery. A 6-volt battery produces a larger deflection. We'll use these 2 voltmeters to demonstrate what happens when a voltmeter of low resistance is used to measure voltage on a high resistance circuit. These 2 potentiometers are hooked in series with a battery, and the voltage across one of them is measured with this electronic voltmeter, which has a very high resistance. When this voltmeter with a lower resistance is hooked up to measure the same voltage, it reduces the voltage it is supposed to be measuring.
RC circuits. This is RC circuits with batteries, okay, and the switches. Charging a capacitor, we switch S to A, okay, and then I assumption. I is the direction, my assumption. And under this assumption, the capacitor top plate as positive charge, and this is negative charge, okay? What, do I have to assume the direction, this direction? No, you don't have to. You can assume opposite direction, and we will get the same answer. If you assume the direction is go to the left, then under that assumption, this should be positive, this should negative. Anyway, now our assumption, the current is from this to right. So this is positive, the negative. Then we write the equation from here. Epsilon minus IR minus V. This V is Q over C equal to 0. Okay. And this I is dq dt. So we put this inside, we get a differential equation. R dq dt plus Q over C equal to epsilon. This is very simple nonlinear first order differential equation. But I guess you have not involved in this content in mathematics. So I'll do it for you to find the answer. Okay. Now, for the differential equation, the initial condition is very important. Different initial condition, same equation, we get a different answer. In our case, is t equal to 0. Before switch S to A, the charge Q is 0. No charge on this one. Okay, this is our initial condition. Then we see we have a Q is this answer. Why? We do the mathematics. Now we cannot do it, but I do it differently for you. Once we know the Q, we know I. I equal to dq dt. We do the derivative of this one. The first term is 0. Second term, you have minus 1 over RC. And the C cancel out, so the current becomes epsilon over R E times minus T over RC. Now this is current, okay? Once we got this, we get the current. To solve the equation, this equation, let me do it in physics. What we do, we say this is dq dt plus q over rc plus equal to epsilon of r. We saw this one. This is constant, there's one linear. So we just look at it and say, hey, a constant satisfies this equation. Because constant, this is 0. And this q equal to epsilon c. What this q is this equation? It is satisfied. So it is the answer of this question. But that's not enough. You should involve in some time. Okay, now we see the second equation answer, we get a Q2. dq to dt, dq equal to 0 without this one, because this one has covered Q1. I solve this equation. This is very easy. So, okay, we move this one. Okay, dq equal to minus Q2. The dt is here of C. And Q2 is over here, you get a dq2 over Q2 equal to dt of RC, integration on both sides. And this one is log of Q2. Okay, and this one is minus T of RC plus constant. And the constant depends on the initial condition. Okay? So this one we can call the Q2 equal to E minus T over RC and plus constant. And the E constant equal to another constant called K. K is another constant. So this equation, we got Q equal to K times E to the minus T of RC. K is a constant, depends on initial condition. Okay, so we see my answer is Q1 plus Q2. How do you know? Now, we put the answer Q in this equation. It should satisfy this equation. See what happened? See, dq dt equal to dq1 dt dq2. This is a constant. This is 0. Right? This is d2. Right? And you see this Q over RC equal to Q1 over RC plus Q2 over RC. And then we put them together. What happened? Now, dq dt plus Q over RC equal to epsilon over R. So these put together, epsilon over R. At this side, look at this one. dq2, dq equals 0. So this is 0. And look at this one. dq, this dq0 plus q1 for RC equal to epsilon t. And we see both sides are equal. So I'll tell you, hey, this is our answer. Q equal to q1 plus q2. Q1 is 6 epsilon. Q2 is k minus epsilon. Now, question is, what is the k? The k is crucial. It depends on initial condition. What is our initial condition? We got when t equal to 0, q equal to 0, right? Okay. Now, we put this one, initial condition. Q equal to 0 and t equal to 0. And when t equal to 0, this is 0. And this is 0, this is 1. That means c epsilon plus k equal to 0. And we found a k. K equal to minus e. And we put this one back. And we get a q. Q equal to ce minus ce e to the minus t over rc. And take the ce out. We get the answer we just saw it before. This is my answer. And current, and we know, is dq dt. Okay, dq dt. This is 0. This is, you have minus minus positive. 1 over rc cancel c. Epsilon r e to the minus c. What happening is, at t equal to 0, this is a 1. I is maximum. And then when t increase to the manifold, the I gradually reduce up to 0. Okay? So look at this one. The Q. The Q is starting from 0, eventually saturate at C epsilon. Okay. We can measure from VC because it is the Q is proportional to VC. So this is a shape. We measure VR. Actually, this is the Q. And the I is dq dt. Okay. When t equals 0, I is maximum equal to epsilon e. When t decrease to 0. And how would we measure VR? Because VR proportional to I, we can get this kind of stuff. The time constant. RC is called the capacitive time constant of the circuit and is presented with the symbol τ equal to RC. In the charging process, it is the time t equal to τ equal to RC, at which the charge on the capacitor has increased to a factor of 1 minus e to the minus 1, or about 63% of its final equilibrium. If this equal to RC, so this equal to minus 1, this is about 60% EC. And when the time is about 3 times of time constant, and we put this equal to C tau, T equal to C RC, we find this charge is already 95% finished. So after that, we don't consider it charging, okay? When the T equal to 4 tau, okay, and the Q is about 0.98%.
This RC board will allow us to demonstrate the charging and discharging curves of an RC circuit. The circuit consists of a battery, a two-way switch, a variable resistor, and a bank of switchable capacitors. When we close the switch this way, current flows through the resistor into the capacitors. Flipping the switch the other way drains the capacitors through the resistor. This oscilloscope will show the voltage on the capacitors as a function of time. Here is the curve with 2 millifarads and 100 ohms resistance. Here is the same capacitance with a resistance of 300 ohms. Now we'll change the capacitance while keeping the resistance constant.
Discharging a capacitor. Now, we just charge the capacitor. There's a positive charge, negative charge. After that, it reached equilibrium, then we discharge it. We switch from A to B. What happened? Now, what I do is, in an established equation, we assume arbitrarily a direction of current and the corresponding polarity across the capacitor for general case. In this case, I assume the same direction as you say that before, okay? And you say, hey, the actual current should go this direction. Yes, I will prove you're right, okay? Under this assumption, I can get the answer. The real current is this direction. Okay. Now, under this assumption, so we get C is positive, this is negative. And we write equation. And the initial condition is another story. So we can get the right answer. We switch. We assume the current this direction. Under this assumption, this is positive, this is negative. And we write the equation of circuit. Okay. We see the Ri. This is Ri. Go this. And plus V. V is Q over C equal to 0. We go this one. Okay. We start off here. R I dq. This against the current. Plus V. This is 0. Okay. And then we see the very simple differential equation. We get a Q equal to Q0 C epsilon. Okay. To the E minus T over Tt. Q0 equal to C epsilon. When it's charged, it's this Q is equal to CV. V is this one. Okay. This is the answer we get. Okay. We look at this answer. At the beginning, Q is full. T equals 0 is 1. As T equals to infinity, this equals 0. Q finally equals to 0. Okay. And then I equal to dq dt. We go this one. We have a minus Q0 of RC equals C. Now see, the real current when T equals to 0 is negative number. So I prove you're right. This is go this direction. Okay? This is I0 called this direction. Now let's see a time constant. Okay, that means about 63% have been finished now. Okay, finished. At 3 tau, that means 95% have been finished. Okay, and only 0.5 left. Okay. Now we see this one. This is what we have to do. Okay, we just discharge the capacitor. Okay, what is happening? You see this one. This is current. The current and connect is goes negative direction. At the beginning, it's very large, and gradually it goes so. This is a current. Okay, and at the moment when switch on, and it means a lot of change. In physical, we mean the frequency is very high. The frequency is very high. You see this one, okay, and this one is 0. This one 0, and the current equal to epsilon of R, and gradually it goes, disappear, vanish. And in this case, the RC resistance at the beginning is 0. Okay, and for a long time, almost equilibrium. In this case, nothing changed. In other words, we say omega frequency change is 0, no change. And this one, the RC is infinity. No current can pass through.
This relaxation oscillator uses an RC circuit to flash a neon lamp at regular intervals. The circuit consists of a 90-volt battery hooked in series with a variable resistor and a variable capacitor. A neon bulb is hooked in parallel with the capacitor. The neon bulb flashes at a regular rate. Here's what happens as the resistance is increased. Here's what happens as the capacitance is increased.
Have you ever seen your house lights dim when you turned on a heater or heavy appliance? We'll use this model of house wiring to demonstrate the effect. 2 resistance wires will substitute for the normal copper wires used in a house to increase the effect. They run ordinary household current into this bank of lamps and heaters, which can be switched on and off individually. We'll first switch on the lamps. Then heaters will be switched on one at a time. When enough heaters are added to the line, the lamps dim. The electrical energy lost in the wires which deliver the current is dissipated as heat.
Simple. As a car rolls along the pavement, electrons move from the pavement first onto the tires and then onto the car body. The car stores this excess charge and the associated electric potential energy, as if the car body were one plate of a capacitor and the pavement were another plate. When the car stops, it discharges its excess charge and energy through the tires, just as capacitor can discharge through a resistor. If a conducting object comes within a few centimeters of the car before the car is discharged, the remaining energy can be suddenly transferred to a spark between the car and the object. Suppose the conducting object is a fuel dispenser. The spark will not ignore the fuel and cause a fire if the spark energy is less than the critical value U equal to 50 millijoule. So that means if the energy is smaller than 50 millijoule, it's safe. Above this one, you will have a spark. When the car stops at time t0, the car ground potential difference is V0 30 kV, very high. The car ground capacitor is C equals 500 picofarad, and the resistance of each tire is R, 100 gigaohm. How much time does the car take to discharge through the tire to drop below the critical value U? Now, we see when you discharge, we have 4 tires. So this is R is 1 of the 4 of this one, okay? So the R equal to total over 4. That's about 25 gigamega, okay? We should write 10 to the 9 mega, okay? The energy stored is equal to Q squared over 2C. We know Q is Q0 e to the minus T over RC. Now you have a square. So this is a square, you have a square over C. And Q0 squared over 2C is the initial U. So the Q has relationship with initial U in this relationship. And Q0 equal to CV0. V0 is 30 kV, okay? C is the capacitance, okay? 500 picofarad, okay? So now we put this one here. Initially, is equal to half CV squared Q squared over C equal to half CV squared. E this one. Okay. Now we calculate UT, okay, equal to half CV squared E minus 2T over C. All right. From this, okay, I get E to the minus T over C equal to 2U over CV squared. And we know that one. This one equal to log 2U over C of C. We put number inside. Okay. So it's T equal to RC multiplied 2U over C. I put number inside. Okay. This is 50, as we mentioned before. So we put everything inside. We get 9.4 seconds. What this means? This means it takes 9.4 seconds for the car to discharge to the safe level. Okay. Unfortunately, during a race, a pit crew cannot wait that long. So what happening? We want to reduce this T. But again, what we can do is reduce the R. Okay. If we have a small R, we have a small T. What we do? Ties for race include some type of conducting material, such as carbon black, to lower the tie resistance and thus increase the car's discharge rate. Sample. A capacitor of capacitance C is discharging through a resistor of resistance R. Question A. In terms of the time constant τ equals RC, when will the charge of the capacitor be half its initial value? This is the Q, we answer. Discharge. I want to find what time, the charge of the capacitor is equal to half. This Q equal to half initial T equal to 0, this is a 1. So Q equal to half Q0. What happened? Then we can find the T. Very easy. Cancel the Q0, we'll take the log, okay, and we get the minus log 2 equal to minus C, okay, and get a T. About 0.69 time constant, okay, you get half. If it is time constant, you get much more, okay. Question B. When will the energy stored in the capacitor be half of its initial value? Now we compare the energy. The energy is Q squared over 2C. And the U equal to Q squared over 2C. And Q equal to Q0E minus T of C. We put this inside. And then make this one equal to original, this one. And what happening? Actually, this one equal to half U0 equal to this one. And then we will find out, cancel out, we get very easy to answer. We find out, we get T, okay, equal to RC over 2 over log C, 0.3, fast. Okay. That means the smaller number than the previous. That means the energy reduced to half ahead of the magnitude of reduced to half. Next chapter, chapter 27, magnetic fields. Welcome you make a comment and give suggestions so that this program can be more helpful. Acknowledgement. This video clip is a part of my lectures on college physics during 1990 to 2021. Based on the adapted textbook, Principles of Physics by Holliday, Resnick, and Walker, published by Wiley. The demo videos were bought from a company in USA by my university for teaching. They helped a lot. I'm sorry for not remembering its name to show my appreciation. It seems that they came from the University of California, Santa Barbara, where I got my PhD in physics. Thanks God.